for soliciting me to participate to this workshop. My talk is a tentative to give a small highlight on the capability of probability theory and statistical mathematical statistics to take into account uncertainties in complex systems. It is not a survey, it's just a part of my works performed with microsource in this field. So, I sit down. So, I will introduce three main approaches: parametric probabilistic modeling, non-parametric probabilistic modeling of model form errors, and statistical surrogate models. Just a few words concerning sources of uncertainties and variabilities. These schemes can be applied to any scale, in computational mechanics or in mechanical. So if you consider a design mechanical system here, you use a mathematical mechanical modeling process to obtain a computational model. This process induces modeling errors or model form uncertainties for the predictions given by the computational model. This computational model has parameters which sometimes are uncertain, and so it's model parameter uncertainties. From this design mechanical system, manufacturing process yields a real mechanical system. So variabilities arise from the manufacturing process and small configuration differences as experimental setups, and so can never perfectly match the design. So I will begin with the first part concerning parametric probabilistic modeling of uncertainties. It's a very big, very broad aspect, so I focus my talk just on the probabilistic model of random fields, which can be used in mechanics of materials. So this type of model is not really simple. Introduced in 2006 for elliptic stochastic partial differential equation, and extended in 13 and more recently in 21. So what is the framework? The problem is to identify a random field as a parameter of differential operator, and for this identification you have to introduce a statistical inverse problem in high dimension. So there is no possibility to directly estimate, identify such random field, such model of random field, without introducing a prior probabilistic model. So if I denote by C using the Voigt notation for the fourth order tensors in elasticity, the capability to identify such a prior model is to introduce a priori fundamental properties such as lower bound, symmetry, positiveness, invariance related to material symmetry, mean value of level of statistical fluctuations, spatial correlation lengths, and possibly support of the spectrum. So I will detail just a bit a prior stochastic model for heterogeneous elastic media with statistical fluctuation in a symmetry class and anisotropic statistical fluctuations. So for X fixed in the domain, this tensor C is in mean close to a given symmetry class corresponding to material symmetry, exhibits more or less anisotropic statistical fluctuations around the symmetry class, and exhibits a level of statistical fluctuation in the symmetry class. So you can remove one of the two last aspects if you want. This slide is a bit complicated, but just for explaining the algebraic construction. So I will explain each term. So the prior representation of this tensor C, represented by metric 6 in Voigt notation, as I said, is written like that. What is CL and what is K? CL is a given M plus valued lower bound field. M plus is a set of all the positive definite symmetric 6 real matrices. K of x, K is the n plus valued random field for which the mean value is k bar. Underline K, I said k bar. E is a mathematical expectation. So what is K is defined by this equation. I will comment each term. What is a G0? A G0 is a random field which is a non-Gaussian n plus valued random germ with mean value, the identity matrix, and for which the level of statistical fluctuation is controlled by a hyperparameter delta 0. The probability measure of this matrix for each given x is constructed using the maximum entropy principle from the information theory, using the variable information. It's not so easy, but the construction is explicit. Now you have A of x. A is a M-sim valued random field whose mean value is A bar, which is a projection in the symmetry class of the mean value of K. So A is related to statistical fluctuation in the symmetry class, which is given. This random field A is written like that, so you know A bar, and now there is an X random field which is N. N is written as a matrix exponential of matrices of this random field N, which is written like that, summation of a J, Yj, Ej sim. Ej sim is a matrix basis coming from basis tensor vapor for describing the symmetry class. N of x is given by this formula, and y of x is a non-Gaussian Rn valued random field, again constructed using the maximum entropy principle, using the information, variable information. And this bar is a normalization depending on these two mean value in order to obtain the mean value given here. So what are the hyperparameters that you have to identify in such a general representation of random field for elasticity? You have 3n spatial correlation lengths for anisotropic part and statistical fluctuation in the symmetry class, and the hyperparameter controlling the level of statistical fluctuation in each part, delta 0 and delta A. And you can include the mean value, if you want, of each random field. Now, I would like to illustrate the use of such a prior probabilistic model for the case of stochastic continuum modeling of random interfaces from atomistic simulations for a polymer nanocomposite and the statistical inverse problem which is associated. So, the objective is to construct a continuum in continuum mechanics. This is a prior model of the elasticity field describing the elastic behavior in the interface domain between an amorphous polymer and a silicon nano-inclusion inserted in the polymer. And the problem is to identify this hyperparameter of the prior model of C using atomistic simulation as experiments for their identification and solving the statistical inverse problem. This work has been performed with Lee and my colleague Johan Diomino from Duke University. This molecular dynamics simulation, I would like that you first time spatial averaging to estimate apparent strain and derive the apparent elasticity matrix in continuum mechanics. And so we look this graph. What is it? The ordinate, the vertical axis, is a polymer to pure polymer density ratio. And the abscissa, the horizontal axis, is the distance R from the silicon nano-inclusion center. So you can see that the diameter of the silica is 6 nanometers, 2 times 3. And you can see that the thickness estimated is between 2 and 3 nanometers. Okay. This is the thickness of the interface. So it's not a perfect interface. So the stochastic, a prior stochastic model of the elasticity field is constructed in the interface for continuum mechanics. You can see the finite element model. This is the inclusion, this is the interface, this is the polymer. And we choose a class as a class of symmetry, a transversally isotropic material in the spherical coordinates. And you use the prior stochastic model presented before. So the hyperparameters are the dispersion parameter, which controls the level of statistical fluctuation, and the two spatial correlation lengths, radial direction and angular tangent direction. So the purpose for the statistical inverse problem, the purpose is to identify the hyperparameter using atomistic calculation using the likelihood method. And what is observed, the random quantities, is the apparent elasticity matrix for all the cells in continuum mechanics. So a stochastic homogenization is performed from the realization constructed with the prior model and with the stochastic boundary value problem. And the evaluation is performed using the likelihood method. What are the results? Just for illustrating, we find that 20% of statistical fluctuation in the random interface, the radial spatial correlation length is a quarter of the thickness of the interface, and concerning the angular spatial correlation length is 3.5 nanometers. And this figure shows the trace of the random field, the C11, a spherical surface inside the interface in gigapascal. The second part is related to non-parametric probabilistic modeling. It's much more complicated because the problem is that when you have modeling errors, you cannot use parametric approach to describing model form uncertainties. So the stochastic modeling concerns operators and not the parameters of the operators. And so for linear problem, linear operator, the non-parametric approach introduced now 25 ago using metric theory was really efficient. But the problem for non-linear operator, you cannot choose this type of approach based on a random metric theory. So more recently, with my colleague Charbel Farad from Stanford University, we have constructed a non-parametric probabilistic approach for non-linear operator, first oriented towards structural dynamics, and after we have improved the methodology concerning the inverse problem. The optimization problem is not so easy. The optimization problem to solve the inverse problem with respect to targets given by experiments. And the last one this year concerns a complete computation of a plane with computational fluid dynamics with turbulence modeling. Just a slide to explain. It's not mathematics. It's just for explaining the concept that is proposed. So I consider Q as a linear or nonlinear operator from DOM, which is a subspace of a Hilbert space H, and I denote by V alpha be Hilbert basis in DOM. So the first case is a construction, a non-parametric construction of a random elliptic operator. And so what is the methodology? We use a Galerkin approach, so we can construct a finite approximation represented by a matrix Qn, projecting this operator on the Hilbert basis V. And so after we randomize the matrix Qn by Qn, the blue, using Maxent. Okay. So it's classical now. Now, what is the construction for the non-parametric approach for nonlinear operator? Again, we construct a finite random family V alpha, which is a second order random variable with values in DOM, a finite family with orthogonality. This means that this family is with values in a compact stiffness manifold. And so when you have, if you arrive to construct such a basis using the Maxent, that is to say, constructing the probability distribution of this family, okay, you can project the nonlinear operator in order to obtain the finite representation U maps to Qn or U, which is a random mapping from Rn into the second order random variable with values in Rn. For instance, to illustrate what is the case of application, you recognize the first part of my talk, the design system, the modeling processing, given a high dimensional computational model, using a reduced model order reduction. And so you have modeling errors in these two steps, and eventually model parameter uncertainties related to the parameterized reduced order system. So this for illustrate this scheme, you recognize the computational model in nonlinear dynamics with initial condition, maybe with constraint equation and observation. So for constructing the reduced order model, we introduce a reduced order basis. We classically use introducing time snapshot and sampling of the parameters and using a POD on this family, this big family, in order to construct a basis represented by matrix V for projecting the system. And so you have these constraints, normalization, V transpose V equal I, and the constraints. And when you replace V by the random family V, you have to construct this family in the compact manifold, stiffness manifold. And so what is the construction? I explain each equation. So V is a ROB, the reduced order basis, which is known. V is a random family associated that we have to construct. What do you see? You see Z, the matrix, random matrix Z. These two equations allow us to stay on the stiffness manifold if Z is the tangent space, which is defined by these two equations. This equation is for putting the constraint equation by B, and finally the jump is U. So U is represented by this random matrix, which is non-Gaussian, and you have hyperparameter. Summarizing with this algebraic model, if you have a random generator of G, which is completely detailed here, you can, all the quantities are known, and so you have a random generator for V. So you know the probability measure related to V. And the hyperparameter are S, beta, sigma, that you have to identify resolving inverse problem. And so if you introduce stochastic error between the target and the response of the nonlinear stochastic form, you solve the optimization problem for minimizing stochastic error. This method has been applied with success in this, for these different cases. The last part of my talk concerns statistical surrogate model. This is part of scientific machine learning. And this tool is probabilistic learning on manifolds for a case involving small training datasets. So we are not in the case of a big dataset in which you use deep learning and resonant network. You cannot, okay? So a small training dataset, for instance, for 40 points, 50 points, 100 points, not 1 billion, okay? So this method has been proposed in 2016 with my colleagues, Roger Ganem from USA, University of Southern California. And so with many extensions concerning physics constraints, concerning by moments or by realization, for incomplete data, non-linear case, and so on, and with many applications that have been published using this type of approaches. So I summarize the methodology before showing an example. What is the framework? We consider a high-dimensional representation of the quantity of interest Q of the stochastic computation model, including discretization of stochastic process and random forest. So you have this equation. And what is these quantities? W is a vector valued random control parameter, for which the probability measure is known, and its support is CW, is known. U is a vector valued random uncontrolled parameter, for which the probability measure is known, and Q is a quantity of interest depending on W and U. What is F? F is a deterministic mapping measurable, which is not explicitly known because it's rather from solving the stochastic problem. And the random graph, so F, capital F, is defined here. The random graph defines a random manifold that is represented by the statistical surrogate model W map to Q, the control variable to quantity of interest, and which is constructed with a joint probability measure, P of Q and W, estimated with a long dataset. The training dataset, I introduce X, which is a concatenation of Q and W. In general, it's in high dimension. Using the solution of the stochastic computation model, we construct a large learned dataset of X using probabilistic learning. And the surrogate model is a statistical surrogate model is based on conditional statistics, constructing the conditional PDF of Q given W. And the probabilistic, this approach has been developed as a dataset. And what is the difficulty? Just a comment. If the training dataset is small. If you use a probability measure corresponding to this small dataset, and if you use any Markovian Monte Carlo, MCMC, for generating sampling from this probability measure, you have a scattering. So you lost the concentration of the measure. But remember, the X is on the manifold, because it's a graph of WQ, but it's a random manifold. It's a family of hypersurface in the Euclidean space, okay? And so the measure is concentrated in this region of the space. And if you have scattering, so you have a sphere of realization, so the support of the learned probability measure is lost. So it is important to introduce additional information for constructing the MCMC in order to discover the geometry of the support of the probability measure defined by the manifold. But the manifold is unknown because you have just a cloud of points. Okay? So the methodology starts from principal component analysis of X in order to reduce the statistical dimension. And the ingredient of the probabilistic this methodology is to project the heterostochastic differential equation, which is the MCMC generator from using the invariant measure on a diffusion map basis. And so the long probability measure is constructed as that. Okay. Just a slide for to show an illustration of the capability of this type of approach to preserve the concentration of the probability measure. For instance, H has dimension 9 after reduction, 9. The training is 400 points and the learning is 400,000 points. And if you see for H1, H2, H3, the clouds of points, you can see that the support, just this section of the cylinder, because it's 3 and 9, is very complex. It's multi-connect support and so on. And you can see, for instance, for H1, the probability distribution is multimodal. If you use the classical MCMC, you obtain these clouds of points, you lose the concentration of the support. So, I finish presenting an application, which is a concurrent method to macroscale modeling on non-random materials, describing like random field, without scale separation. Without scale separation. So this is a work performed with and always my colleague from Duke. And the framework is the following. We have a multiscale nonlinear simulations. This is a soft biological tissue, and which introduces a strong coupling between the macroscopic at the structural scale domain and the microscopic scale without scale separation between micro and macro. So, look this scheme just for fixing the idea. This is a structural domain composed of 9 macro domain. Each macro domain is omega mac and omega meso at each point C of macro is a statistical volume element with characteristic length, in this case 0.25. So this biological tissue is an hyperelastic compressible and isotropic material following the Kirchhoff model. The first Lamé parameter is modeled by a homogeneous random field, and a Dirichlet condition is applied on the boundary of the structure. The formulation for the change of scale, the formulation is the following. The multiscale stochastic nonlinear PD is formulated with deformation gradient tensor F and the first pure Kirchhoff stress P. And the localization is performed solving this nonlinear stochastic boundary value problem. Y is a displacement field, F macro is a stochastic deformation defined by localization, and the apparent stress tensor at macro scale is obtained by spatial averaging. Maybe I could say psi I for each integration point in the statistical meso volume. For the probabilistic learning, the pair FP is replaced by the pair CS, the right Cauchy-Green and the second pure Kirchhoff stress tensor, because it's symmetric, so it decreases the number of freedom. And the objective is the construction of a statistical surrogate model of the non-local homogenized response on nonlinear elasticity. Donc, W maps to Q. And what is W? W is a discretization of the random field, a random displacement field of the boundary of the macro domain. And Q is a set of all the Cauchy-Green deformation and the stress and the deformation tensor and the stress tensor at the quadrature points in the macro domain Xi. So, just finishing with this slide. What is this slide? This slide is a validation of the proposed methodology. The horizontal axis is the indices of the quadrature point in the macro domain. The three top figures correspond to the mathematical expectation for stress and strain deformation. And for a given value of the control parameter, that is the displacement of the boundary, and for composant J, 1, 2, 3 of this tensor, and for performing this comparison, an extensive computation has been performed without simplification, using 20,000 realizations of the random field, requiring 2 million of nonlinear finite element computation. And when you use a surrogate model, the gain is 40, the speed up is 40, but if you use 50 realization, the speed up is about 100. And when you compare the dashed line with solid line, you can see that the prevision is good enough. Thank you for your attention.